So, let us look at this again, the life cycle embodied energy of repair. So, as I was saying, all deterioration process in reinforced concrete, when you look at, they finally cause cracking, expansion of the material inside and cracking, and finally cover concrete get exposed. For example, I mean the reinforcement get exposed. For example, if it is freeze thaw reaction, right, the water freezes and there is little more complex mechanism, but I am not going to this. So, water freezes inside the concrete in cold area and ice occupies more volume than the water, it exerts pressure, and this process also causes cracking. Over a period of time the cover concrete will come out, there is basically you will find initial some cracks, then some kind of removal of the cover, slices of concrete will come out sort of. So, cover concrete comes out. So, the moment reinforcement get exposed, it is now it is bare and it has got no protection, will corrode finally. So, basically when I want to do a repair, most of the time I will be requiring to replace either the full element is another thing, but cover. So, an assumption here is made is that you are replacing the cover, and if it is a slab, both sides, this is an overestimation, but it is okay, conservative way, and this is the depth of the section. Now, how many times you will repair this? Because I said that supposing my process of this typically the scenario time, let us say, and this is the condition, right, or material degrades, or material degrades and elements will deteriorate. So, the terminologies are, so degrades or deterioration, let us say deterioration, initially deterioration is 0, its condition, let us say, or something like that, and then for some time it will not show anything, may not show anything depending upon the type of deterioration, but after that it will start deteriorating and there is a level after which I can't accept it. If the crack has come, I can what we call serviceability limit. So, it has reached the serviceability limit, crack has appeared at the surface of the beam or column element, I can't accept it, I have to do the repair. So, when the crack has come onto this one, these are your reinforcement and the crack is appeared here, visible cracks are there, then I got to do repair. Now, I will be repairing the cover concrete. So, if I repair, I bring it back, same repair I do, I will bring it back and again it will go and again you do it, right. You might be doing it a number of times. How many number of times you will be doing it? If this is my intended design life IL, which is for buildings could be around 60 years, and this is the basically repair life, right, this cycle, repair cycle, this cycle, then number of times I will be doing it is, number of time I will be doing it, this is service, S stands for service life actually, service life of element, number of times for service life of the element, or D is a cover, then that many number of times. So, for example, if its life is 60 years and every 10 years I have to repair, 6 times I will repair it, right, and every 6 times I will replace this much of concrete. Original section had this much. So, total proportion of the concrete that I will replace during its life cycle because of repair is given by this equation. And if you know the initial embodied energy, simply assume that same amount of energy will go again, same amount of energy will go, but there is a proportion, because this is the proportion of the cover compared to the whole section. IEE was calculated for the whole section, now I am doing it only for the cover, and this many number of times I am doing. So, this is the embodied energy of repair, embodied energy of repair, embodied energy of repair. As many number of times I do the repair, it will go that. That means, this is a point. If I make it more durable concrete, which does not show up that kind of my is more sustainable, that is also an issue, your embodied energy required will be less. So, that is what it is. So, life cycle embodied energy is then the sum of these two, life cycle embodied energy is the sum of these two, initial embodied energy and embodied energy of repair, right. So, now this I can equivalent carbon I can find out, equivalent carbon I can find out from, I know the embodied energy, I can equivalent carbon I can find out, right. Now, this carbon equivalent carbon is not taken in account of the carbon dioxide that has been already emitted by in the cement production, that is separate. I am not talking of carbon dioxide production, I am only looking at the energy that is gone in. But this energy, supposing a part of it is fossil fuel, part of it is fossil fuel, that will add to carbon. So, we know that would depend, it will vary from nation to nation. A nation which uses most of its energy not from fossil fuel will have much less here, because if you are using electricity for production and transport, supposing you are transporting by rail and it's electrically driven rails, this could be different than where let us say it's a diesel locomotives which actually does most of the work. So, one can calculate this out. Now, carbon equivalent of fossil fuel, you remember I said this earlier, is 0.02 kg per megajoules, 0.72 kg per megajoules. This was obtained from 1984, a figure of this much petajoules of energy was used from fossil fuel in the world. See, there are people who did all kind of accounting. Now, this is a laborious work, it needs a lot of workforce to do all this job and collect the statistical data and find out. So, this is 260 petajoules, released 5.2 billion tons of carbon dioxide, right. And then from this one can calculate out 1 megajoules, 1 megajoule will produce how much carbon dioxide, this is 5.52 billion. So, in fact 0.02 kg per megajoules. So, because I think I have done this calculation once before 2600, so I do not think I will repeat this now. So, this calculation we have done. So, 0.02 kg per megajoules. Now, supposing the one case, India is somewhat different now, supposing 65 to 68% obtained from fossil fuel and rest from hydroelectric and nuclear power, right. Now, so this would be for cement, this is 1, because cement production, all the energy that we use, majority, I mean it will be 95% energy comes from fossil fuel. You mix pet coke or furnace oil with the raw feed and then burn it, right, clinkerization process. You cannot use electricity, uniformity, there is technological issues, chemical technological issues are there. So, for cement this is 1, but for other one, supposing we get 65 to 68% from fossil fuel and rest from hydroelectric power, nuclear, solar energy, etc., then you multiply the total energy by this factor except for the cement. Say, let us say fossil fuel ratio is 0.66. In fact, it is said in India it has now got reduced, because we have started using a little bit more solar energy, right. At least Solar Energy Society of India that claims quite a bit. They say that we are using, so as more the renewable energy use, this value will go down. I mean less the fossil fuel use, this will go down. So, this part is, so when it comes to concrete, of course, this part we know, that unburnt lime, etc., that production we know separately. So, equivalent life cycle carbon emission one can find out. Then you can take the carbon dioxide from the cement also, because in the repair also you will use cement. So, one is from the energy, so one from the energy, other from the other from the fossil fuel part of it. So, you see if I know the fossil fuel ratio, initial embodied energy plus repaired energy, this into 0.2, because 1 megajoules, so this is expressed in megajoules, let us say 1 megajoules produces this much amount of carbon dioxide. This is for energy of repair, etc., but for cement this is energy of repair, but for cement I have to multiply, I won't multiply by this by 0.66 or whatever, I will have to multiply by 1, and this is 1 plus the repair part, 1 plus the repair part, and if the fossil fuel ratio is 0.02 multiplied by you know the 0.14, how does it come? 0.14, because 0.14 is the carbon dioxide produced from 1 kg of cement, because 56 carbon you know 56 56 is what, 40 plus 16, so calcium oxide. So from 56 grams of calcium oxide produces 12 carbon. So this is carbon equivalent, not carbon dioxide equivalent, carbon equivalent, because this is carbon equivalent. So everything they are putting it in carbon terms, not in carbon dioxide term. So carbon terms, and if you calculate this out, so this multiplied by 0.66, because 0.66% is calcium oxide in the system, not calcium carbonate, so I am taking from calcium oxide. So this is 0.14, and that is where it comes. So 0.14 C into 1, that cement you have used, plus additional carbon dioxide coming from there, coming from the repair part. So total carbon dioxide that comes out from the cement is this. In addition to this, initial embodied energy of repair, and initial embodied energy plus this is for the repair part. So this is the direct carbon emission from calcium oxide production, and here when you are using the cement, this fossil fuel factor would be 1. So this is not a constant fossil fuel factor. For rest of the thing it could be 0.5, 6 or whatever it is. This can vary from 0.5. Some country uses 50% only fossil fuel. Rest all comes from elsewhere, alternative fuel, you know, or nuclear or hydel solar energy and all that, renewable sources and so on. So this would vary, and for cement, this energy, part of this energy is, majority of this energy in cement production is, this ratio is nearly 1, because you are using directly fossil fuel. So one can, yes, this is what I am saying. So therefore one can in fact, if you make a reference concrete, you can even compare different concrete, because life cycle energy you have looked into, not embodied energy in terms of carbon, life cycle energy in terms of carbon production, that is what you are looking, or life cycle carbon emission if you call it, right. So that you can compare with a reference if you have established one, that okay, how good or how bad, or you can compare two concretes, which is better, which is worse. You can compare two concretes, which is better or worse. For example, if I use more fly ash, for example, if I decide to use more fly ash here, it will have this 0, because remember I gave you the energy of production of all of them. Fly ash is available as waste. So transported. For example, if I use instead, let us say GGBFS, which will have somewhat less than cement, it has got some values. I gave you a table 372 or something from cement, or relative values are there. So if you use more fly ash, this will be lower. If you are using some natural sources of water, as it says, the production energy will not be there, transportation energy will, and if you are close to the source, then also transportation cost is going to be lower, right. So the point that how do I calculate the data is a problem. Generally one is to, every nation or every zone, every area has to generate if they want to do this kind of an accounting. It is a laborious process, but that can be done, right. So that is it. As I said, there is a table available in net, Bath University has done for UK all. I do not know whether I have kept the table here, but that does not mean much, because it is only information. So that information you can collect. They have collected done for lot. In India it is very less, few, I will show you that. So equivalent life cycle carbon emission is given in this equation, equivalent life cycle carbon emission, and this is how it is. The other issue is natural resource depletion in concrete production. So far we talked of carbon, but sustainability must take account of, remember I just gave you one slide, I said that it must also look into depletion of natural resources, right. So if your aggregate, coarse aggregate is natural, fine aggregate is natural stone, energy will go definitely there, then the proportion of natural material depletion is this, because this is a concern. Many places sand is not available now, the fine aggregate is difficult to get. So you have to use them judiciously. Point is that you will be using, but you have to use them judiciously. So, as I said that in UK they have open cast mines. So, it's leased out and they produce scientifically. Even in India there are people now, what is it called, manufactured aggregate. So, manufactured aggregate comes from crushed stones, but in a computer controlled, through a computer controlled process which will maintain the shape best suited for concrete production, and sizes as desired, more uniform within the size itself, within the size fraction itself. So, that would make more efficient use of the natural depletion would be less. So, this is a factor for natural material depletion. AC is the amount of coarse aggregate, AF is the amount of the fine aggregate, F is pozzolana or supplementary cementitious material, and then if you are using total, it is trying to find out the total material which is there in the system. S are quantity of concrete ingredients, other industrial byproducts if you are using, then that gives you an advantage in the total volume of the material as much as industrial byproducts you are using. So, this factor gives you an idea of how much natural resources depletion is occurring, right. Okay. Yes, this is fine aggregate, right, quantity of coarse and fine aggregate, that is what it is, and coarse aggregate, fine aggregate may be super plasticizer or something I might have added, but that is also a small quantity that does not go. But supposing I am using some other material and any other industrial waste material. So, this is total proportion of this natural aggregate will be, natural material would be less, and therefore, depletion ratio will be less. Now, that is what I think I did not mention, now I am mentioning how you find it out. Statistical analysis published data of energy used by industry. Supposing I know the accounting is done in cement production, they do accounting of the energy, how much energy they have used, from what sources, electricity, from board electricity authorities and all. And construction site, supposing this is done, then you can, some of them are published. Energy don't mind publishing, but financial thing they may not publish it so easily. Then input output analysis relies on economic input and output of the nation. If nationally, if you are looking at economic input and output, money flow and to from energy producer to each sector of industry. For example, in Delhi it is supplied by BACS, right. So, if it wants to find out how much is going on to the residential area, but I am talking of cement and concrete industry, it can be true for anything else. Supposing there is an industrial area where we are producing, there cement is being produced also. So, if the authority electricity supplying agency tells us how much energy was consumed by the all cement factories, electrical grid, and those kind of things. So, collecting data from there. Systematic, then process analysis, if you want to do systematic examination of direct and indirect energy input to the process, high effort required, but one can estimate them, and possibly one can do a research sort of thing to see how it is changing with time, get some ideas and things like that. Generally one can use combinations, so generally one can use combinations, right, generally one can use combinations. So, concrete sustainability issues, cement and carbon, that is what we have looked into. Efficient cement use, quality and admixtures, they help, we will see that now next. Efficient aggregate and water use, and of course, modern concretes, they can be sustainable. Modern concretes can be sustainable because you have, as I said, you have varieties of concrete today, which I showed once, I I will come back to this again. Contribution of concrete towards operational energy saving, that is of course in buildings, that is only for buildings. So, all these issues are concrete sustainability issues are there. So, if I am looking at sustainability of concrete, I must look into all these issues actually, right, all these issues I should look into. Okay. So, quickly we will look into first steps out from there. First step out from there, cement and carbon we have looked into. We will look into quality and saving of material, some of them we will look into quickly. I will look into that. Start this, and then quality has got a role. Quality of construction. Why? We do not talk of quality so much for other material, but we do talk for concrete. The reason is concrete has been produced largely manually or semi-engineered way. For using this kind of thing which you might have seen, something of this kind, quite common. Quite common is this. You might have seen something like this. There is a you have a tilting drum mixture of this kind. Discharging concrete, rotating, right. You would have seen this kind of mixture which is very common. The volume would be very small, quantity per batch. Now this concrete you add manually, you add aggregates. I mean, it might have a small batching plant, and if you add even water manually, then it is a disaster, because unless it is, supposing it is a controlled batching plant, things should be better, the proportions will be maintained better. So you will not get variation from point to point. If it is done, this is semi-engineered concrete. So semi-engineered concrete, I will not call it engineered concrete, semi-engineered concrete, as opposed to a computer controlled batching plant. But there the cost might be slightly higher, but in the long run you will improve everything. Number of repairs required will be less, and even in the beginning you will require lesser material. Let us see how it is. So quality is an important issue in terms of sustainability also, right. So quality is very important issue, because it can reduce your cement consumption. Right. So this sort of mixer machine we talked about. By the way, mechanization is not new in concrete, as I have mentioned maybe in some time if you have taken a concrete technology course, where we talked about RMC. First RMC truck was actually used or developed or invented, I would say in 1903 in Germany, something of the similar kind, but actually it got after the war, many countries it became very popular, Second World War I mean. So it is about 100 years now easily, and many countries do not use any. It is difficult to find a small mixture if you want to use them, except for one or two repair. Now the implication of quality, let me look at it. I will just take a few more minutes for you. Supposing I have batching done manually, then if this was my cement quantity, this was my water quantity, this was aggregate quantity, this was fine aggregate quantity, and then I might have had another F and etc., etc. Now I cannot, in any measurement, I cannot get C all the time. Any measurement, any process you use, there will be some sort of tolerances in the balance itself. There is a least count of the balance. So there is always error in measurement even in batching. Now higher this error, so sometime you will give C plus delta C, sometime it will be C minus delta C. Water will be delta W plus minus. So amount of water will be again W plus delta W or W minus delta W. And if you know from concrete science, W by C controls the strength. So one case you will have C, let us say very low, and let us say extreme case this is very high. So one extreme would be W plus delta W divided by C minus delta C. Other extreme will be W minus delta W and C plus delta C. Similar problem will be there, similar kind of delta plus minus delta C plus minus delta AF etc. will be there. So, if you can see in this case the strength will be high, in this case strength will be low, right, because higher the water cement ratio, strength is lower. So, where my delta W is plus, this is the highest water cement ratio, this is the lowest water cement ratio, right, isn't it. So, this will have highest strength, this will have lowest strength. Now, if my delta C is small, this will have less spread, this will have less spread. So, that is what I am talking of. So, concrete strength is normally distributed. If you do large number of cube tests, cylinder tests or whatever it is, you will find they follow this sort of bell shaped curve, right, that is normally distributed. Now, the standard deviation is lower if you have these values lower. That means you have a better control, you are not mixing by not by just guess. In semi engineered concrete sometime water somebody will put it like that without even measuring it properly, or if you are doing it volumetrically with a can of this shape can, okay, there is a mark, you fill it in water up to this and put it. Now, this cannot be accurate, visually seen, and which you have to see even not in a transparent glass or perspex glass or something. So, spread should be more if you do site mixed manually. So, site mixed manual concrete is something like this. But if you have ready mixed concrete with a computer controlled batching plant, you will have spread lesser. Now, what is the implication? Your structural design is based on something called FCK. FCK is characteristic strength, the strength that will be exceeded by 95% of the sample. So, this is FCK, and how is FCK related to this mean strength? This is related by this formula. Mean strength is FCK plus 1.65 standard deviation. So, if my standard deviation is higher, I will need more. That means, if my quality is bad, if sigma is larger, I would need more mean strength, which means more cement and lower water cement ratio. So, that is the issue, because water cement ratio dictates the strength. Typically, I can draw it like this, right. So, higher water cement ratio, lower strength, and lower water cement ratio, higher strength. So, if I have water to cement ratio I am talking of, so in this case I might require here, if this case I might be able to operate with this, provided I am satisfying the other requirements, durability etc., etc. So, therefore, you see I am going to use less cement in this, which means more sustainability, So, if you work on better construction or better production process, more mechanized production process, you will be saving on to your cement, and it is definitely cheaper in the long run and also more sustainable. So, that is the issue of quality, that is the issue of quality. I think we will be just stopping. So, this is just variation in properties of the material, variation in proportions, variation in mixing process, variation in compaction quality, all these add to the standard deviation. So, if you can control more and more of it, you will be actually making concrete more sustainable, right. So, mechanization gives you better. So, I think we will stop at this point. If you have some questions, I will take.